the strength you lose, attenuation is much higher in case the frequency is higher. In this case, I'll be giving you a particular table which you just make a noting as far as the frequencies are concerned, relationship, frequency, and the raindrops, attenuation. Higher the attenuation, I think more the range, higher the frequency, more is the attenuation of the raindrops in case of this particular energy, because the frequency used is much, much higher. As such, the energy loss also is much higher. And this relationship is here. If the wavelength is 10 centimeters and above, we are talking about the attenuation in the range of the radio energy. In case the wavelength is 10 centimeters or more, the losses are almost negligible. If the wavelength is anywhere between 10 to 4 centimeters, the losses are significant. And if the losses are less than 4 centimeters, the losses are very, very significant, very high. There are three ISS. One is more than 10, in between 10 and 4, less than 4. So as far as the losses of the raindrops are concerned, we have very heavy losses in case, as it is, because the frequency used in the radars are very, very high. As such, we fall almost in the last category. So we, as a crew, as a user of the radio energy, if you are using some sort of a radar on in your aircraft, you must be very careful when you have a patch of rain in between you, or in case you are passing through a particular rain, you'll find that the received strength is either very less or almost negligible. Any questions, sir?
Yes, sir.
Now, in case you remember, can you anybody in the class recollect what is super refraction or duct propagation? Also, we gave it there's another name, duct propagation or super refraction. This was discussed in the class much earlier, actually.
When waves travel through a different medium of different density.
Yes. Yes.
And the waves tend to change in direction.
Super refraction is duct propagation is applicable to in the VHF and higher frequency bands. At times, due to various atmospheric conditions, where you have the ionospheric layer in the atmosphere, and there's a decrease in the humidity with the increase in the height, that particular sector, you have something known as super refraction, where the range of any system increases manifolds. This is called duct propagation or super refraction. Applicable, as I said, this is applicable to VHF and higher frequencies, is very much applicable in the radars also. At times, because of the super refraction, even if you have got a maximum range of say 20 kilometers, there will be a radar who will pick you up at even 1,000 kilometers. This is part of the super refraction. As such, in case you have super refraction in the atmosphere, there is a possibility that you might pick up an aircraft which is much further away than your maximum range, what is depicted in your system or what your system actually projects tell you. This is called super refraction or duct propagation, where the atmospheric conditions at times are such that the range automatically increases manifolds. Okay. Any questions? Anybody in the class has got not understood? Now we have already discussed the very basic principle, how the bearing and range are measured. Bearing is measured by what we term as the torchlight principle or the searchlight principle, where you rotate a radio beam in a clockwise manner, covering all 360 degrees. and any object which comes in between when during the rotation of this particular radio beam will give you the direction, and the pulse radio or the echoes will give you the range of the radar. Now, my question to the class is, what if you are sitting on a radar screen? Suppose you are sitting on the radar screen. What sort of picture image is created of an aircraft on your screen? If you happen to be sitting on a particular scope where you are seeing the radar picture being painted on your radar screen, what sort of picture you feel is painted on the radar screen to give you the image of a picture aircraft? What sort of picture is normally painted? What do you feel? I'm sure none of you have seen the radar screens, but what do you feel sitting in the class? What do you feel is the picture of a thing being painted on the radar screen? It's not mentioned. It's not mentioned. It's not mentioned. This is called radar resolution. Yeah, you can go up slightly. Further scroll. No, further up. Other way around. Other way around. Go up. You're going down. Up. More further. Oh no. Okay. Carry on. Radar definition. Minimum radar. No, you're going in the other direction, sir. You are going on the basic. Go. I think it's almost page number 11 or 12.
Oh, 11. Okay. 11.
Maybe.
Oh, this one. Okay. This one, sir?
Yeah. Pulse repetition. Yep. No, carry on further. This is no. Go down further. This is the radar antennas. Antennas is the next thing which you are going to teach. Before antennas, please.
Okay.
Or further go down. Or further down.
This one is page 13.
Yeah, to go down further, 11. Go further down, please.
So this one is page 14, sir.
Yeah. This is no, further down, please. Further down. No, other way around.
Can you give the exact number of it?
I think page numbers are different. We are talking about radar resolution now.
This one is CRT already.
No, this is next page. No, this is.
This marsh grass.
I think it's on page 10. Radar resolution is page 10.
Page 10.
Page 10,
this
yeah.
one,
Further, yeah. Go back.
Yeah.
This one. This is. Yeah.
Okay.
Now, this is what we are talking about. The radar resolution is the type of picture painted on the radar screen. Right? Normal image is some dot or some aircraft shape is painted on the screen of the radar, and the color of this actually it is a sort of a rectangle which is called radar rectangle, which is painted on the screen, which is green in color. The length of this particular so-called picture painted on the screen is length of the radar of the rectangle is half the pulse length. The length of this resolution or this picture which is painted on your screen happens to be half the wavelength, and the height of the rectangle is depending on the width of the beam, on which is called the beam width. Beam starts with a very narrow beam will start and keep on widening if it goes further away. That means if the aircraft happens to be far away from the radar head, the height of the rectangle will be much higher. This is called radar resolution. Radar resolution is the picture painted on the screen, light green in color, rectangular in shape. The length of the rectangle is half the pulse length, and the height will depend on the beam width. The higher you, beam width means the closer you are, the narrower will be the radar picture, and the further away you are from the radar head, height will of the radar resolution will be much narrower. Now, in the beginning, we spoke, or some time back, we spoke about as far as the picture painted on the radar screen is concerned. Our requirement is that the beam width should be as narrow as possible, so that especially in radar, the beam width has to be very narrow, because you would prefer picking up one particular object at any given time. The advantage of obviously is that the energy is concentrated to a very limited area. As such, the picture painted on the screen happens to be very effective and very good. The narrower the beam, the better resolution you have. To make the beam narrow, you have to change. The larger the antenna, the narrower is the beam. When you talk about the size of the antenna, narrow, that we are talking about the diameter of the antenna. The larger the antenna, the narrower is the beam. Now, this facility or this privilege is possible only on the ground. You may change the size of the radar antenna depending on what sort of resolution you want. But you can't possibly do this in the aircraft. Aircraft, because of aerodynamic limitations, you can't possibly vary the size of the antennas. As such, this particular privilege is available only on the ground. And the other way to make the beam narrow is increase the frequency. Higher the frequency, narrower is the beam. Questions, please. Doubts, please. Clarifications, please. No? Okay. If you have no questions, then I talked about, yes, sir.
Sir, so back on the second statement of yours, the larger the antenna, the narrower is the beam.
Yep.
Okay, so which means you say that this is related to the ground radar.
With ground, no, this is applicable to in all radio activities, anywhere.
Okay.
But more applicable in radar. What I said is that on ground, it is possible for you to vary the size of the antenna. You can make it smaller, you can make it larger. But in the aircraft, it's not possible. Aircraft has got aerodynamic limitations as far as the size of the various items are concerned. In aircraft, you can't vary the size of the antennas. You can't make them larger. You can't make them very large.
Okay.
But these are the limitations.
Okay.
So the other way to make the beam narrower is increase the frequency. Higher the frequency, narrower will be the beam.
The beam. Okay.
Right? Now,
okay.
yeah.
So which means our objective to narrow the beam is to get the better pictures on our radar screen, is it?
That's right. That's right. But this is not our problem. This is the problem of the people who are actually manufacturing those. We as a crew should be knowing this is the process, this is the procedure. We are the users of all these so-called services which are made available. But you as a crew should be knowing that this is what the requirement is to make the beam, why the beam should be narrow. The narrower the beam, the better, obviously, the resolution. When you talk about resolution, it is the painting on your radar screen, right? It's called the radar resolution. As I said, the color is light green, and the size of the picture painted is rectangular in shape. The length of the rectangle is half the pulse length, and the height of the rectangle depends on the beam width. That means the closer you are to the radar, the height will be smaller, and as you keep going away larger, the beam width becomes larger and larger. As such, the height of the radar, of the resolution also becomes larger and larger. Now, one of the aim, especially in radar, what you want, would you prefer is that your screen, radar screen, should be as clean as possible, as clear as possible, so that you can identify the aircraft very easily. Now, every station, whenever you have a radar system, there are certain things which are permanent in nature. Maybe a building, maybe a hill feature, which is obviously permanent in nature. You have made the radar applicable to a particular aerodrome or a particular area. You have put the system there. In this particular system, you will have certain buildings or certain constructions or certain things which are permanent in nature. And if the radar aerial goes, circles around and throws the radio energy, obviously all these buildings, etc., will also be reflected back and they'll be reflected onto your screen. Your screen will get cluttered up with things which you actually do not require. This system is called MTI, Moving Target Indicator. MTIs are installed in all radar screens. And the purpose of the MTI, Moving Target Indicator. And the purpose of the MTI is to remove, nullify all the permanent echoes. The building which is permanent in nature, that particular echo is automatically removed. It does not reflect on your screen. If you have got a building which is permanent in nature, that also, by use of MTI, use of a particular circuit, which is called jittering the PRF, as such, you create a situation where all the permanent echoes are permanently removed. Your radar screen stays as clean as possible. This particular process is called Moving Target Indicator, MTI in short, that the permanent echoes, whatever buildings, whatever construction, whatever hill features you have, in the close vicinity of the aerodrome where your radar screen is moving around, it's picking up all the items which are permanent in nature, and we jitter the PRF, or we do some technical process which is called jittering the PRF. As such, we remove all the permanent echoes from the screen at one time. So once you see your screen is as clear. All these permanent echoes around are automatically removed by using a circuit which is called MTI, Moving Target Indicator. And the process is called jittering the PRF. Questions, doubts, clarifications? Now, next we talk about the radar antennas. Now, there's a lot of research in progress as far as the radar antennas are concerned. And as I said, the main aim of the exercise when we talk about the antennas is we have to transmit the beam which is narrower, narrower, and narrower. The type of energy which is used, and we have something known as, in case you see on your screen, move further slightly, slightly more, please. Slightly more, yeah. Here we have, let's go down, go further, no, other way around. Yeah, here we have something known as, these are called the side lobes. You can see those narrow balloons in the corner here. They are called the side lobes. We want the radar antenna should be such, because this is a waste of energy. This is a waste of radio energy. As such, we do not want the side lobes, or we want to reduce the size of the side lobes as far as possible. As such, we keep carrying on various types of radar screens. Radar aerials are being used today. Basic purpose is that the radiation pattern should be such that you have the main lobe is as narrower as possible. That's all. Questions, please, if you have any. Otherwise, we move on to the next subject, which is called CRT, or the cathode ray tube. Next page, please. Yeah, this is yeah, just slightly up. No, slightly other way around. Yeah, slightly up. Yeah. This is what is called the CRT. That's all. CRT. Yeah. This one. I want the picture. Yeah, this picture only. This is called the CRT, or the cathode ray tube. Very similar. I mean, The main, why do we have a CRT in the whole system is basically because electronically you have the measure, when you talk about the timing in the radar, the time of transmission and the time of reception becomes very relevant in basic radar theory. If you consider the radar theory, when you talk about the time interval between the transmission and reception, there are no other means to measure this time except electronically. We are talking about microseconds now, and we have got no method of measuring this particular time, visually or physically by clocks or watches, etc., etc. This is certainly not possible. As such, we have to measure this time electronically, for which we have generated or created, which is called the CRT or the cathode ray tube. The basic purpose of the cathode ray tube is to measure the time interval between the transmission and the reception. This is absolutely like what you have, a TV at your residence, TV at your home is absolutely very similar to that particular TV. And this happens to be, in front happens to be the so-called screen of the CRT. What is happening behind the screen is shown there, and it is called the cathode ray tube. I'm not going into much detail of this cathode ray tube, but it just generates, what it creates is the time circuit on the screen, which when you talk about the transmission, time of transmission and the time of reception, automatically a bulge comes onto the particular screen, and which gives you the time interval between the transmission and the reception. Basically, how the system works is at the other end of the screen is what we got is something known as a cathode. Cathode, whenever heated, it generates certain amount of ions, certain amount of atoms. It creates atoms, and these atoms, if you keenly see, there is a sort of a small opening. This cathode ray is covered by a metallic piece, which has got a very small opening. All these atoms which are being generated by the heating of the cathode ray tube are concentrated onto the center so that they can go out from this particular tube. In between are the various sort of methods of focusing the cathode ray, whatever atoms are being generated onto this particular screen, so that the screen gets lighted because of that. Now you can have straight line, you can have a circular time circuit, whatever you want, and these are the so-called in between. You got something known as reflector plates. You can reflect, you can change the voltage of these reflector plates by moving the beam up or down, whatever direction you want, whatever you want to do. Depending on these two different type of plates, one is moving left and right, the other is moving up and down. Depending on the choice of type of time base you want on the screen, you can change the voltage of these particular radar plates, and accordingly change the time base, which is called the time base, circular or maybe rectangular in nature, or maybe straight line in nature, depending on what you want, what type of image you want on your screen, what type of radar you're using, what type of method, instruments, information you want from that particular screen. You can change the timing on this, and accordingly it's fitted onto this. This is called the cathode ray tube, basically to know the time interval between the transmission and reception electronically. Otherwise, it is not possible for you to measure the time. There are no other means except electronically. And in the radar, we use something known as CRT or the cathode ray tubes to get this particular information. Anybody, any questions so far? No questions, and then we'll go slightly further. Do I class at 11 till 12:30 today?
I
Hello?
think until 11, 12, 15, right?
12:15. You say whatever time you want. I have nothing much to say in that.
We started this class earlier, right? So
11:15,
so 12:15.
yeah.
12:15.
12,
Okay.
15.
Another 15 minutes, that means, right?
All right.
Okay. Right.
Correct.
Move forward. We move forward. We go to the next place, which is called the PPI, Plan Position Indicator. Just move further. Keep moving further. We come to a place which is called the PPI, the Plan Position Indicator.
This one, sir.
Carry on moving.
Please.
Carry on. I'll tell you. Yeah. Further down, please. Further. Yeah. That's all. This is called the PPI. Now, PPI means what we are trying the type of screen you have in front of you where the radar information is displayed. There are various methods. You can have rectangle, you can circular, you can have any shape you want. But the most common type of indicator today, which is in use in radar, is called PPI, Plan Position Indicator. You have a circular in front of the radar scope, or in front of the observer, the chap who's observing the radar screen. There is a circular sort of a dial, which has got all the markings right from 000, 090, 270, etc. The complete markings are there. And you have something known as a baseline or the time base, which is the center. And you have these range circles depending on what range you have selected on your particular radar. You can select 50, you can select 100, you can select 150, depending on the maximum applicable range of the radar. Plan position indicator, in front of you, there's a small circular scope with all the markings and whatever time base. Outside, you have something known as an aerial or the antenna, which radiates or transmits the radio energy. This particular time base, you have what you see is synchronized with the antenna outside. That means if the antenna is facing 090, this particular time base will also face towards 090. They are coordinated and they are synchronized regularly, and you see that whatever direction the time base is facing, or whatever direction this particular antenna is facing, your time base will also face in that particular direction. Now, during this revolution of the radar screen, if any object is picked up by the radar, that will be marked on the time base. It will be marked depending on the range you have selected. Now you know that you have got an object or you have got an aircraft which is on bearing of 12055 nautical miles. As soon as this particular radar picks up, the same picture will be projected on your radar screen, giving you the range and the direction of that particular object. PPI is the known as Plan Position Indicator, is the name of the system which is most common as far as the radar information display is concerned. You also will be using these PPI when you talk about the weather radar, etc., etc. Similar display is there in the aircraft also for you to project to find out which direction a particular weather exists. Okay.
Okay,
Can
sir.
we move? Can you move slightly forward now? We talk about the classification of the radar. Important, you must understand and appreciate what we are going to discuss now.
This one, sir?
Go back, please. Yeah. This is what we talk about. Yeah. We talk about the various classifications of the radar. Go slightly back. Just after PPI, just after the PPI. Yeah, these are the classification of the radar system. Now, these radars are classified into three different categories. One is called the primary radar. The other is called the secondary radar. And the third is the radar, which is, of course, continuous frequency changes there. Three types of radars in use. One is obviously the primary radar. The other is the secondary radar, and the third where the frequency changes at regular intervals. Now, what is the difference between the primary, secondary, and the which is called the continuous wave radar, where the frequency keeps. I'll discuss these all three. Basic difference between the primary, secondary, and the continuous wave radar. The basic difference is in the case of the primary radar, you transmit and receive the information on the same frequency, same aerial can be used. You transmit and you receive. Primary radar is a radar which transmits and receives information on the same frequency. Secondary radar, you transmit on frequency A and receive the information back on frequency B. There are two different frequencies for transmission and reception. In case of the continuous wave radar, we keep changing the frequency at regular intervals at a known particular rate. You transmit a continuous radio wave, but you keep changing the frequency at a known rate. These are three different categories as far as the classification of the radar system is concerned: the primary, the secondary, and the continuous wave radar. In the secondary radar, question please. Any question, any doubt, any clarification required here? Or can I
Can
move
you
forward?
repeat the continuous frequency radar?
Continuous wave radar, you transmit the radio in the form of a continuous wave and keep changing the frequency at a known rate. Primary radar transmits, receive same frequency. Secondary radar transmit and receive information on two different frequencies. And in case of continuous wave radar, you transmit a continuous wave. No, you don't transmit pulses now. You transmit radio wave in a continuous manner, but keep changing the frequency at a known rate. The three types of radars.
So on secondary radar, you mean you transmit in one frequency, but we receive in other frequency?
Yeah, I'll brief you as far as the secondary radar system is concerned. In the secondary radar, we have something known as an interrogator and something known as a transponder. Interrogator is the initial transmitter which asks questions, and this is received by the transponder, and transponder gives a response on a different frequency altogether. Primary radar and the secondary radar. So primary radar, you transmit and receive on the same frequency. In case of the secondary radar, we transmit and receive information on two different frequencies. And one is known as, one part of the secondary radar is called the interrogator, and the second part is called the transponder. Interrogator asks questions, transponder responds to the question, but on a different frequency.
Okay.
Primary, secondary, and now we will be discussing these primary and secondary radars much more in detail a bit later. But when we talk about the classification of three types of radars: primary, secondary, and the continuous wave radars. And primary radar, same frequency. Secondary radar, you transmit and receive on two different frequencies. It has got an interrogator and a transponder. And once you interrogator initially transmits, it is received by the transponder. Transponder gets triggered and replies back on a different frequency altogether. We will discuss the advantages and disadvantages of primary and secondary radar, or maybe continuous wave radar also, in case time permits today, otherwise maybe in the next class.
Is one advantage of primary radar?
Yeah, advantage of primary radar. Now it is when you say it is self-contained. What do you mean? Can anybody in the class say advantages of the primary radar? It is self-contained. What do you mean by self-contained?
system.
It works on its own.
It works, that means it's not depending on any other system to assist, to help. As far as the primary radar, it's totally on its own. It transmits on its own, receives on its own. With a different frequency, doesn't make a difference at all. These are the advantages of the primary radar. It's self-contained. It does not require any outside source to help. Like in the case of the secondary radar, if the transponder does not respond, the system will not work. But primary radar doesn't have this particular so-called disadvantage. It is it's totally on its own. Peak power transmitter can be made very high owing to the relatively short time of actual transmission, but more power is required. That means in case of the primary radar, basically, idea is that the echoes coming back should be strong enough. So you have to have a very powerful transmission for the echoes to come back should be stronger enough. A common area, obviously, you can have one aerial there. And obviously, you can vary the size of the antenna so that you can make the beam as narrow as possible. Questions, doubts, clarifications. Then we talk about the so-called secondary radar, right? As I mentioned, in the secondary radar, you have something known as an interrogator and something known as a transponder.
Okay.
We will be discussing, there are two aspects which we'll be discussing in the secondary radar. One is called the DME, Distance Measuring Equipment, and the SSR, which we'll of course discuss maybe in our next classes, whenever we have them. But these are the two aspects as far as the primary or the secondary radar is concerned. Now, in secondary radar, as I said, the advantages of the secondary radar would be, can anybody guess one of the main advantages of a secondary radar? No, don't go through the, just try and think. What could be the advantages of a main advantage of the secondary radar?
Faster.
Yeah, go ahead.
Faster. Is it? It will be faster because there's two transmitter and receiver, so we don't have to wait for the pulses to return.
No, here pulses are not required to be returned here. In other words, what we are saying, what you are trying to convey here is that the power required is very less. We are not dependent on the reflecting surface, whether it is wood, metal, etc., 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 etc. You transmit the radio energy, it triggers the transponder, and the transponder responds to that particular question. So the power required obviously very less because the radio wave is traveling only one way. Two-way travel is not required. You are transmitting, it is received by the transponder, and transponder is carrying out a fresh transmission on a different frequency. So the power required is very less. It's one-way travel of the radio wave, and the reflecting surface type of metal, etc., etc., does not make any difference. Number two advantage of the secondary radar is on your radar screen, reflections from the ground, other object reflection, etc., are not there because your receiver is tuned onto a frequency which is entirely different than the frequency on which you are transmitting. So no ground reflections, unnecessary, etc., etc., will come back onto the screen. Right? Can anybody in the class read what are the secondary radar advantage, difference between primary and the secondary radar? Can anybody in the class read, please? Not advantages. I'm talking about basically what is the difference between these two. Unlike primary radar, the operations of the secondary radar depends on the active cooperation of the other object. Right? What does it mean? It means that if I transmit, if the interrogator transmits, and the transponder does not respond to this particular question, the secondary radar system will not work. In case of the primary radar, it's totally self-contained. It doesn't require help of any other source. But here you do require some assistance from this particular source. Or the second part is the secondary radar information is exchanged in form of grow. Yeah, another point which everybody should note, in case of the primary radar, you transmit one pulse at a time. And unless that pulse comes back, the second pulse does not go. Not required in case of the secondary radar, because you are depending on the fresh transmission from the transponder. As such, you transmit not in a single pulse, but you transmit in a group of pulses. In case of the primary radar, one pulse at a time. In case of the secondary radar, as said, interference with the radar is reduced because I said you are using two different frequencies, etc., etc., etc. Different frequencies. Now, advantages of the secondary radar. Please slightly go back.
Okay.
Yeah. Advantages of the secondary radar. Can anybody in the class do a bit of reading, please? Anybody in the class?
You mean read the paragraph?
Yeah. Please read the paragraph. I'll try and explain that, please.
Advantages of secondary radar.
Yeah. Go ahead.
So you mean read loudly or
Yeah,
just
read loudly,
back?
please. Read loudly so that I will explain then.
Okay, there are various of them.
Yeah.
Sorry, sir.
You go ahead. Read.
Okay. There are various of advantages of using secondary radar over primary radar. First and important advantages is the power requirement. With the type radar, it is possible to work with much lower power. There are two reasons. A, the signals are doing only one-way journey. And B, there is no double scattering to come back as in primary radar.
Yeah.
Second,
Good.
because of the use of different frequency, the ground transmitter will not pick up ground reflection on transmitting frequency. Similarly, the airborne transmitter will not pick up its own ground reflections.
Yeah. In function to whether it is reduced.
So first is about the power requirement.
Yeah. But all this actually we have discussed in the class now. As far as the advantages of the system are concerned, system shape requirement is because you are not interested in what shape, what size of the object is reflecting, because the transponder is giving a response to the questions, right? Continuous, can you go the last chapter, please? Last part is the continuous wave radar. Yeah, as I said, in the continuous wave radar, you transmit a wave in a very continuous form, but the only difference here is that you don't transmit on a fixed frequency. You've got a range of frequency which you can vary, and the rate of change of frequency is known. That means the time interval between the transmission and reception can be found out on what frequency you transmitted, on what frequency you received the information. The rate of change of frequency is known. As such, that can be converted to time. The main advantage of continuous wave radar, it has got no minimum range problem. It can start from zero. It has got no minimum range problem.
Okay.
Right?
Yes.
Now I have finished with the lecture today. Now we have about, I think, 14 questions based on the radar. I would like you people to do this as your homework. And whenever the next class is, we will discuss these question answers. And thereafter, we'll go on to the next topic of distance measuring equipment. Any questions, anything you want to know? Anything which you have not understood, which I have tried to explain, I will try and explain it now.
Okay, sir. Anyone?
No.
Good.
If no questions, thank you very much and stay healthy, stay fit. Look after yourself,
you, sir.
take care. And
Thank you,
I'll be
sir.
there.
Sir, please don't
Thank you,
go out.
sir. Stay safe.
Thank you, sir.
Okay.
Stay at home, sir.
Bye-bye. All the best.
Bye, sir. Stay at
Have
home,
fun.
sir.
Bye, sir.
And I'll
Have a nice
see you
day.
after
Thank you,
tomorrow.
sir.
See you day after.
Okay,
Yes, sir.
sir.
Thank you, sir. Bye-bye.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
sir.